welcome to the third part of our unit on oscillatory motion and waves. In this unit, we're going to think about graphing the motion of simple harmonic oscillators. And to do that, we're going to begin by considering a mass on a spring. Now, the analysis we're going to do here is going to be in terms of a mass on a spring, but it actually holds for all simple harmonic oscillators. For this, dreadfully sorry. For this, I'm going to draw some pictures, and I'm going to think about the motion at each point. So here, this is just an edge for me to have as a reference. This line is going to be my equilibrium position. And then I'm going to draw two more lines, one to either side, that are equally spaced from the equilibrium position, roughly, as good as I can do. So what I'm going to do for the motion is I'm going to pull, I drew that on the wrong spot, so we're going to try again. I'm going to pull the block out to this line here. And this is as far away from equilibrium as it's going to go, which means this line is the amplitude. At this position, all of the energy is going to be elastic potential energy. And the force on the mass is going to be given by negative Ka because of Hooke's law. Remember, F equals negative Kx. And at this position, it's not moving. When we release, it starts moving. And eventually, the block gets to the equilibrium position. At the equilibrium position, it is moving this way. And the velocity is as big as it's going to get. And that's because all of our energy now is kinetic. The force, the net force on the block here is 0 because we are at the equilibrium position. It's then going to move through the equilibrium position, continuing moving in the same direction, and eventually will hit this bar, which remember was equilibrium or equidistant from the equilibrium position. So this is also a distance a. If you want to think about it as negative a, that's cool. And at this point, we again return to a 1/2 Ka squared for our energy, and our net force in this case will point in the other direction. So if the first one was negative Ka, this one has to be positive Ka. This position I'm going to call my t equals 0 position. If you think about the motion, once I'm to here, what it's going to do is basically turn around and start heading back out. So I can draw the series of pictures here for it moving the other way, and then it hits the equilibrium position again. Again, gets Vmax. Right? So this position is halfway through one cycle. So this time would be the period divided by 2. When it hits equilibrium the first time would be the period divided by 4. So now take this, which is drawn kind of crudely, and let's look at it in terms of a simulation, which I already have up over here. So you can see instead of a block, they're working with a ball, but that's okay. The green arrow gives you the direction of the force, and at the moment, it is as pulled out as it's going to be for this oscillation, which means graphically, the first position that is measured will be up here, positive. I will let it go a couple of oscillations. Okay. So here we are, and we see that this has a period of about 6 seconds. So as expected, when it hit the maximum at the other side, that was about 3 seconds, halfway through. And the first time it crossed equilibrium is about 1/4 of that, which is 6 divided by 4, 3/2. There you go, about 1.5. Okay, this is the graph of position as a function of time. Now, I'm going to reset it. Instead of thinking about the position, think about what the velocity is doing. So remember, initially the velocity is going to be 0, and then it becomes bigger, then it becomes smaller again, and then it changes direction. So if I plot the velocity versus time, it starts as 0, and we can again see the period of about 6 seconds. Now let's think about the acceleration. At the endpoint, the acceleration is going to be in the direction of the net force and will be as big as possible. Since this is set up with positive going this way, that means our initial acceleration will be negative, and then it will oscillate, hitting 0 at the equilibrium position. If the position graph is a positive cosine, then the velocity graph is given by a negative sine function, and the acceleration graph is given by a negative cosine function. So what I want to do now is think about what is the value of the maximum velocity, what is the value of the maximum acceleration in terms of the parameters associated with our mass on a spring system. So we're going to begin by thinking about conservation of energy. And we saw in the analysis we did at the very beginning that at an endpoint, all of our energy was elastic potential energy. And at the equilibrium point, can't spell, all of our energy was kinetic energy. At the endpoint, the elastic potential energy was 1/2 Ka squared, and at equilibrium, it was 1/2 mv max squared. I can cancel out the 1/2s, and I get v max squared equals K over m a squared, or in other words, the maximum velocity is the square root of K over m times a. In general, remembering from what we've done thus far this unit, omega was the square root of K over m. That means that I can write the maximum velocity as omega a. And this is true for all simple harmonic oscillators. If I now think about the forces, at an endpoint, the net force was as large as it was going to be. That was given by negative Ka. But remember, the acceleration was in the same direction as the force, so I can write that as mass times a negative acceleration to put it in the same direction. So the negative signs cancel, and this is the maximum acceleration because I'm at an endpoint. So the maximum acceleration is going to be K over m times a, or in general, the maximum acceleration is omega squared a, remembering again that omega was the square root of K over m for a mass on a spring. Again, this result that the max acceleration is omega squared a is true for all systems that undergo simple harmonic oscillations. With this information, I can now make plots of position, velocity, and acceleration as functions of time. So I'm going to draw my position graph at the top. So it starts high, goes around, And if I draw things properly, which I haven't quite done because I'm graphing by hand, but we'll work with it for the moment. At this time, I've gone through one period. My x or my y-axis is x. We'll do it in meters. It oscillates between a and negative a. And my x-axis is time in seconds. I can now make a graph that corresponds to this motion for the velocity in meters per second. As we saw in the simulation, the velocity starts at 0 at an endpoint and is going to be opposite in direction to the displacement, so it is a negative sine function. And I'm going to try to get this aligned, so bear with me for a minute. Okay, so it goes down, it comes up, it hits a max there, and continues around. Not the prettiest sine function, I will be the first to admit. The max and min are Vmax, as we just found. Okay, so remember Vmax was omega A. And now, lastly, I can do my graph of acceleration in meters per second squared as a function of time. Don't forget your axis labels. Again, I need my pretty lines to help me line things up. And as we saw in the simulation, it is a negative cosine, which means it's going to start negative, come up, go up, come down, and it oscillates between A max and negative A max. Not the prettiest. I admit, not the prettiest. However, I can make them prettier. And the way I can make them prettier is by pulling up the Excel spreadsheet that I made with the graphs. So the nice thing about this is that you can play around with what is the period. That'll give you the angular frequency, and then that will automatically change. So right now I have a period of 3. If I change it to 4, it auto updates and graphs correctly. So we have a period of 4. It completes one oscillation at 4. It starts at 4 and oscillates between 4 and negative 4. That's given by the amplitude. If we go to the velocity graph, it is a negative sine, and notice it's oscillating between something around 6 and negative 6. That's because Vmax is going to be 1.5 times 4, which is roughly 6. Okay. And then lastly, we can look at the acceleration, which is oscillating between 10 and negative 10. So we come up here. We need to square this. 1.57 squared. It's a number I don't know off the top of my head, but I will get it. 1.57 squared is roughly 2.5. If I take 2.5 times 4, I get 9.8, or roughly 10. So that's why that oscillates between negative 10 and 10. We still have a period of 4. I will put this Excel sheet in the resources associated with this unit. It's actually already up in the resources folder for math or general help materials. I will also link it into the lesson for this week so that you can look at this and play around with the graphing and see how things work. I am going to expect that if I give you the graph, you can identify A, Vmax, A max, period, and omega, angular frequency. You can pull everything off the graphs, if you will. I'm also going to expect that if I give you information, you can make the graphs and identify the correct graphs. Okay, so thus far in our analysis, we've considered things that oscillate perfectly. I release it, it's going to go forever. Let's instead go to a more real-world example, because in the real world, we have friction. So we're going to look at the simple pendulum here, again, instead of the mass on the spring, because I don't have a mass on a spring with damping. I guess I do. It's right here. There we go. So if I play it again, it's going to do exactly what we saw before. I'm going to reset it. And now I'm going to make it more real world and put some friction in and see what happens. Hit play. And you can see it no longer oscillates between 1 and -1. It is slowly losing amplitude because of damping, because of friction. Now, take a minute and think about your car. There's actually a great deal of effort that goes into making cars to get this fine-tuned perfectly. If it damps too quickly, so I will reset, I will damp it really, really quick. You get barely one oscillation out of this. Okay, so if this were your car, this would be a car with super duper stiff springs. You go over a bump and thwump. It hurts, right? On the other hand, if the springs in your car are too soft, then you go over a bump and a good bit of time later, you're still going over the bump. Your car's still oscillating up and down. So there's a lot of effort that's put into fine-tuning the springs in your car so that you don't get your bones jarred by having too much damping, and you don't have too little damping, which means, 10 miles later, your car's still oscillating because it went over a bump. So that is damped motion. The other type of motion is called forced motion or driven motion. And when you have a forced motion or driven motion, you have to apply a force on an oscillating system at its resonant frequency. A good example of this is pushing a kid on a swing. If you don't push at just the right time, then the child's motion doesn't grow, which is not something we normally do. We normally let the child swing back to us and we push him forward, and we match our push with the oscillation frequency of the child on the swing. Another good example of a driven motion is the Tacoma Narrows Bridge. The Tacoma Narrows Bridge spans a body of water. I don't remember exactly what one it is, in Washington. And the first bridge that they built had some unfortunate design characteristics. Now, I'm not going to show you this entire YouTube video. However, I will show you a little bit so that you can see what we're talking about here. Okay, I'm feeling kind of silly right now because the Tacoma Narrows Bridge is a bridge over the Tacoma Narrows. That should have been obvious. Okay, moving onward. So I said this bridge had some design flaws. The design flaws was that it had two oscillation frequencies that were very close together. It had one that caused a torquing motion and one that was an up and down oscillation. And what happened, to the best of what we've been able to determine, is that as the wind that went down this portion of the Tacoma Narrows passed over the bridge, it caused little vortices, which also just happened to be very near those two oscillation frequencies. And it drove the bridge so much that in general it was given the name Gallopin-Gertie. And on this particular day, got the oscillations going so very well. You can see the torquing oscillation here very nicely, the twisting one. It got them going so well that there's a beautiful video here where the whole bridge collapsed. Right? It could not withstand the large oscillations due to that driven motion. This concludes this portion of this part of this unit. Wow, that was a lot. In the next part, we are going to take our knowledge of oscillating systems and actually think about waves.